Let's look at another type of assignment problem, which is the traveling salesman problem. Consider a scenario where you are planning for a vacation to visit 5 cities: A, B, C, D, and E. Suppose the location of all these 5 cities on the map is as I'm drawing here. So A is here, B is here, C, D, and E. Now you have to visit each of the cities only once. The trip should be continuous and you should come back to the city from where you started. So how will you go about finding the shortest route to cover all the cities? So here you can travel from A to C and then from C to B, but you can't come back from B to C. So you will have to travel from B to E or B to D. So the first step would be to capture the distances between each of the cities. So you need to capture distance between A to C, A to B, A to D, and A to E. Similarly, you will have to capture the distances between B to A, B to C, B to D, B to E. After you have gathered this information for all the cities and all distances, then you can use the Hungarian method to get the shortest route. So let's see how we can solve a real life problem using the Hungarian method. A salesman has to visit 4 cities: A, B, C, and D. The distances in 100 miles between each part of the cities are given in the matrix. If the salesman starts from city A and has to come back to city A, visiting each city only once, which route should be selected so that total distance traveled by him is minimum? And what is the total distance traveled by him? So as you can see in the matrix, you have 4 cities: A, B, C, and D. These 4 cities are listed in the from city column as well as in the to city. So if you look at the first box, it says the distance between A and A. So this is 0, of course, because it's the same city. Now the second box says the distance between A and B, and that is 4. The distance between A and C is 7, and the distance between A and D is 3. Similarly, if we then go to the second row, the distance between B and A is 4, between B and B is 0, the distance between B and C is 6, and the distance between B and D is 3. Similarly, the distances between C and each of the other cities and D and each of the other cities is listed in row number 3 and 4. Now if you note in the matrix, you'll see that you have zeros in the diagonal line here. What this means is that since the distance between A to A is 0, B to B is 0, C to C is 0, D to D is 0, the distance is mentioned as 0. Now basically what this means is that the salesman should not travel to these cities from the same city. So in order to find the shortest route, we'll have to first express this data into an n by n matrix. So let's move to step number 1. So step 1 is to express the matrix into an n by n format. Now since the salesman cannot travel from one city to the same city, and it should not be in one of the solutions, let's assign a very large value of infinity in each of the elements along the diagonal line. So then our matrix will look something like this. So as you can see, for this diagonal line here, I have replaced all the zeros with a very large number, that is infinity. Since this diagonal line cannot become a part of the feasible solution, and since assignment models are primarily minimization problems, by assigning a very high value of infinity, the chances of getting any of the diagonal line values in the final solution has been eliminated. So now let's move to step number 2, which is to deduct the smallest element in a row from each of the elements in that row. So let's move to step 2 here. Let's copy the shell of the matrix. Now let's go row wise and find out which is the lowest element in that row. So in the first row, 3 is the lowest element. So let's deduct 3 from each of the elements. So infinity minus 3 remains infinity. 4 minus 3 is 1, 7 minus 3 is 4, 3 minus 3 is 0. Similarly for the second row, the lowest number is 3. So we get 1, infinity, 3, 0. For the third row, the lowest element is 6. So we get 1, 0, infinity, and 1. And for the fourth row, the lowest element is 3. So we get 0, 0, 4, and infinity. Now let's move to step number 3. In this step, we'll repeat the same steps that we had done in step number 2, but this time we'll go column wise. So let's first copy the shell. So for the first column, the lowest element is 0. So 0, if we deduct from any of the elements, it will remain the same. So let's copy all the elements as it is. For the second column, again we have a 0. So let's copy the elements. For third column, the lowest element is 3. So let's deduct 3 from each of the elements in that column. So 4 minus 3 is 1, 3 minus 3 is 0, infinity minus 3 is infinity, and 4 minus 3 is 1. For the fourth column, again we have a 0. So let's copy the same elements. Now let's find out if we have achieved an optimal solution or not. So let's move to step number 4. Let's first copy the matrix that we had achieved in step number 3. Now let's cover all zeros with the minimum number of straight lines. If the number of straight lines is less than the number of rows and columns, then we have not achieved the optimal solution. However, if the number of straight lines is equal to the number of rows and columns, then we have already achieved the optimal solution. So since we have 4 rows and 4 columns, let's first go row wise to see if we have any row with 4 zeros. So first row has only 1, so let's skip this. Second has only 2, let's skip. Third has 1, fourth has 2. So none of the rows have 4 zeros, so let's try column wise. First column has only 1, second column has 2, third column has 1, and fourth column has 2. Now let's again go row wise, and this time let's try to find if we have 3 or more. So none of the rows has 3 or more. Let's try column wise. None of the columns has 3 or more. Now again let's go row wise, and this time we'll see if we can get 2 or more zeros. So the second row has 2, so let's draw a straight line here. Third row has 1, fourth row has 2 again, so let's draw a straight line here. Now let's go column wise to see if we can get 2 or more zeros in any column. So first doesn't have any, second has only 1, third doesn't have any, and fourth has only 1. Now let's again go row wise to see if we can get 1 or more. So first row has 1, so let's draw a straight line here. Third row also has 1, so let's draw a straight line here as well. So now the number of straight lines required to cover all the zeros is 4, and the number of rows and columns is also 4. So basically the optimal solution has reached. So now since the optimal solution has been achieved, let's move to step number 5 to perform the assignments. So let's first copy the matrix that we had achieved in step number 4. Now to make the optimal assignments, we'll go first row wise to find a row with one exclusive 0, and we'll make that assignment. So let's go to the first row. Now the first row has 1 0, so let's assign this 0. Now since D has been assigned to A, D cannot be assigned to any other cities, so let's cross off all other zeros. Now let's move to row number 2. So here also we have one exclusive 0, so let's assign this 0. For row number 3 we have one exclusive 0, so let's assign this. Now since we have assigned this 0 here, column B cannot be assigned again, so let's cross off this 0. For row number 4 we again have only 1 0, so let's assign this. So here our assignments are A to D, B to C, C to B, D to A. So if the salesman is starting from A to D, and from D he is going back to A, so this does not meet our criteria, as the salesman has to visit each of the cities before coming back to the city from where he started. So here the salesman started from A, visited only D, and then is coming back to A. So basically this assignment does not solve the problem. So now let's try to find the next best optimal solution. So in the matrix, let's find out which number is higher than 0 but the lowest amongst all other numbers. So we can see that 1 is the next lowest number. So let's try a different combination of assignment. So let's first copy the matrix. Now since there are many cells where we have the number 1, let's choose any one arbitrarily. So let's first take the number which is appearing the first. So let's assign this 1 here between A and B. So since 1 has been assigned, let's cancel this column and this row. Now let's proceed to make the assignments. Let's try to find the rows with one exclusive 0. Now the second row has 2 zeros, so let's skip this. Third row doesn't have any 0, so let's skip this. Fourth row has one exclusive 0, so let's assign this. Now let's proceed column wise to find one exclusive 0. So A is already assigned, B is already assigned here, C has one exclusive 0, so let's assign this C here and let's cancel this 0. So now we don't have any zeros for row number 3. So if we go column wise, first column has already been assigned, second column has been assigned, third column has been assigned, fourth column is remaining. Now in the fourth column we have only 1 for the third row. So let's assign this 1 here. So now basically our assignment becomes A to B, B to C, C to D, and D to A. In other terms, we have A, then B, then C, then D, and then the salesman returns back to A. So this looks like a feasible solution. We are covering all the cities, we are visiting all the cities only once, and we are then returning back to the city from where we started. So let's now note down the distances. So A to B from the original matrix is 4, B to C is 6, C to D is 7, and D to A is 3. So the total distance that the salesman will have to travel is 20 miles.